Hello, my name is Varun Chandrasekaran, and I'm here to present our work on exploring connections between model extraction and active learning. This is joint work with my collaborators, Kamalika, Irene, Somesh, and Songbai. Back in the day, the user had access to some data and could train a model locally. With the increase in data, the user now requires additional computational support for training. The user ships this data to the cloud and waits while the model trains. On completion, the user can issue a prediction query to the cloud. For example, the user sends a photo of a cat and the cloud responds with the label cat. Additionally, the model stored on the cloud can be made public and can be accessed via a query interface. The advantages of such an approach are scalability, availability, prevalence, and monetizability of the model. That is, each query made to the query interface pays the user a fixed dollar value. Consider a scenario where a large organization wishes to train a model to cloud and make it publicly accessible. An adversary can interact with this cloud-hosted model and pay some money for each query it issues. The adversary observes the responses and learns another model. The objective of model extraction is for the adversary to learn an approximation of the model with as few queries as possible. Once the adversary extracts this model, it can proceed to create adversarial examples of white box knowledge, undermine the payment ecosystem as it has a local approximation, or perform more sophisticated attacks such as model inversion or membership inference to learn the sensitive training data. An example of model extraction in one dimension can be done using simple binary search. Here, the cloud-hosted model contains a half-space denoted by the character W. The regions on the right are labeled +1 and the regions on the left are labeled -1. The adversary issues paid queries and observes the responses. These responses contain both the label and some auxiliary information defined below. Observe that the adversary can easily find the point where the labeling region changes from -1 to +1 through a simple binary search. This simple example highlights the importance of auxiliary information in the extraction process. To provide model extraction attacks, prior works make several assumptions. First, they assume that the cloud service provider responds to queries with both the label and some additional auxiliary information. They also assume that the cloud service provider is oblivious to the attacker's existence. Finally, for models like decision trees, they assume that each component, such as a node, is uniquely identifiable. Additionally, prior work does not give provable guarantees of convergence and rely on several heuristics. However, in the real world, none of these assumptions hold. Cloud service providers could deploy defenses involving some randomized procedure or return only the hard labels for any inputs provided. These hard labels can contain no auxiliary information whatsoever. The adversary may not even know the nature of the model that is being hosted on the cloud, let alone whether its internal subcomponents are uniquely labeled. In our work, we focus on the first two real-world constraints. Let's take a step back and discuss active learning. Active learning is a form of semi-supervised learning where there are two entities, a teacher and a student. The student interacts with the teacher through issuing several queries and observing the teacher's responses. At the end of this interaction, the student learns a concept. It is well known that for some hypothesis classes, active learning has a lower query or sample complexity than passive learning approaches. Better still, we know the number of queries needed to learn some hypothesis classes. Model extraction involves the interaction between an adversary and the cloud service provider. At the end of this interaction, the adversary learns an approximation of the model hosted on the cloud. This process is awfully similar to active learning. Once we have established this connection, the only pending question is, what are the queries that the adversary needs to issue to learn the approximation? Several candidates exist. The first strategy is to pick queries or data points to be labeled from a pool of data. The second strategy assumes that the adversary has access to a similar data set as one used to train the model. Third assumes that the adversary has access to a seed data set which can be augmented to increase the number of samples. However, all these strategies assume that the adversary has some knowledge of the model or the task it was trained for. Alternative strategies involve generating random data or using some predefined strategy to synthesize queries de novo. In our work, we consider the last two strategies. That being said, we can make the connection that model extraction is similar to a particular type of active learning, query synthesis active learning. The formal connection is in our paper. Here is a teaser of some of the results we have. For linear models such as Halfspaces, we provide an extraction algorithm that operates in the hard label setting. This spectral algorithm synthesizes queries that enable efficient extraction. For the same linear models, we also provide an algorithm when the service provider deploys a defense mechanism, that is, label randomization. Inspired by version-space learning, our approach is resilient to such a defense strategy. For nonlinear models such as kernel SVMs, we utilize the active selection procedure of BORD. Our approach is more sample efficient than that of prior work and learns a model of comparable accuracy. Refer to our paper for more details. We also show how model extraction is inevitable. Specifically, both data-dependent and data-independent mechanisms, such as label flipping, fail. In particular, the data-dependent randomization, such as data-dependent label flipping, fails for more traditional passive learning-based attacks. The results on 3 different data sets show that passive learning enables precise extraction. This extraction is measured by the geometric error measure. However, this extraction is at the expense of substantially more queries. Let's discuss one other result, the extraction of decision trees. Like prior work, we assume that the cloud service provider does not provide identifiable nodes or operate on partially complete inputs. One natural candidate for extraction is the algorithm proposed by Kushlowitz and Mansour. However, this approach is not ideal. We utilize the importance-weighted active learning strategy using inputs generated from a uniform distribution. Observe that our approach achieves comparable accuracy to the oracle. In this more restricted regime, we require an order of magnitude more queries in the worst case, but are still able to learn a comparably performant tree. In summary, we establish a connection between active learning and model extraction, and are able to provide attacks with provable bounds. Our attacks are in a more realistic setting compared to prior work. Finally, we also highlight a theorem that states that model extraction is an inevitable outcome even in the hard label setting. We encourage you to read our paper for more details. Some open questions remain. The first is understanding if one can design an active learning algorithm in the query synthesis setting for deep neural networks. There exists work in the pool-based setting, but none in the query synthesis setting. The second is determining the nature of the model hosted on the cloud through just this hard label interaction. This is truly a challenging problem. Finally, we wish to understand if active learning-based model extraction attacks transfer. That is, if the cloud provider is hosting a DNN, Can the adversary learn a decision tree that is comparably performant? Please reach out to me or any of the other authors for any questions you may have. Thank you.